This multiple choice final exam review is for those of you who are taking the first semester of organic chemistry. So let's go ahead and begin. Number 1, which of the following functional groups is not found in the molecule shown below? For each of these questions, pause the video and work on the problem first. See if you can get the right answer. And then once you have selected your answer, unpause the video to see the solution. So let's go ahead and begin. Our goal is to find out which functional group is not found in the molecule. So let's identify all the functional groups that are in the molecule. So what is this? What functional group do we have here? CHO. This is equivalent to this expression here. That is an aldehyde. So therefore, we can eliminate answer choice E. Now what about this functional group in the middle with 2 oxygens? What is that called? That functional group is known as an ester. An ester has this general shape. It has a carbon with 2 oxygens, and it has an R group, one attached to the carbon and the other attached to the single bonded oxygen atom. So that's an ester. After that, we have an NH2 group. This is known as an amine. You can also write it as RNH2. So D is out of the question. What about this group? This OCH3 group? What functional group is that? So notice that we have an oxygen attached to 2 carbons, which is basically equivalent to an oxygen attached to 2 R groups. This is known as an ether. So A is eliminated. Next we have a COOH group. That is known as a carboxylic acid, which if you write it out, it will look like this. You have an R group, and then you have a carbon, which is double bonded to an oxygen, and it has an OH. So that's a carboxylic acid, and this is an ether. Now the carboxylic acid is not listed as an answer, so we don't have to worry about that. Next we have this OH, which is an alcohol. So C is eliminated, which means that B is the right answer. And what about this group? What is this group called? So as you can see, if you see a carbon attached to an NH2 group, that's an amine. If you have an NH2 group attached to a carbonyl group, that is known as an amide or amide, which is not listed. So therefore, answer choice B is the right answer for this problem. Number 2, what is the IUPAC name for this compound? Is it A, is it B, or is it C or D? Well, let's find out. The first thing that we need to do is we need to identify the longest chain. So let's begin counting from left to right. This is 1, 2, 3, 4, 5, 6. If we go to the right, it's 7. But if we go up, it's 8. So that is the longest chain. 8 carbons is associated with octane. So we could eliminate answer choice D and C because the parent name is heptane. Now here's a question for you. Should we count it from left to right or right to left? If we count it the way we have it, notice the substituents. We'll have a methyl on 3, a methyl on 6, and an ethyl on 4, which correlates to answer choice B. B has an ethyl on 4 and 2 methyls on 3 and 6. Now, if we count it the other way, notice that we still have a methyl on 3 and 6, but we have an ethyl on 5, which correlates to answer choice A. So do we want the ethyl to be on 4 or on 5? You want to count it in such a way that the substituents have lower numbers. So therefore B is the right answer. So you want to count it in this direction. So when you name it, you want to start with ethyl, since E comes before M. And then we have a 3,6-dimethyl. And then because we have an 8-carbon chain, it's octane. If you recall, methane is associated with 1 carbon, ethane 2, propane 3, butane is 4, pentane is 5, hexane is 6, heptane is 7, octane is 8, nonane is 9, and decane is 10. So B is the right answer for this problem. Number 3, which of the following carbocations shown below is most stable? So what do you think the answer is going to be? So go ahead and take a minute and work on this example. Now, what we need to keep in mind is that tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. And the reason for this is due to the inductive effect and hyperconjugation. In the inductive effect, the carbon atoms, which are electron donating groups relative to the positive charge, they can donate electron density to the positive charge by means of the inductive effect, that is, through the sigma bond. So that's one way they can donate electron density to a starving carbocation, which really wants electrons. The other way is by means of the overlap of atomic orbitals, which is known as hyperconjugation. So let's say if you have a carbon atom with a plus charge, and let's say there's another CH3 group, and so here's a CH bond that's next to it. So there are electrons in this orbital, and that orbital can overlap with the empty p orbital below it. And so that's how electron density can be donated to the carbocation by means of hyperconjugation, which is through the overlap of atomic orbitals. So when these two orbitals overlap, electron density can be shared. So those are the main reasons why tertiary carbocations are more stable than primary ones. A tertiary carbocation is basically a carbon that has 3 other carbons attached to it. And the carbon in the middle has a plus charge, so it's a carbocation. So that's why it's called tertiary, because there's 3 carbons attached to the carbon with a plus charge. And so the more methyl groups that you have next to the carbocation, the more electron density that can be donated, which means you have a more stable carbocation. Now, what about allylic carbocations? A secondary allylic carbocation is more stable than a regular secondary carbocation. An allylic carbocation is one that has a plus charge 1 carbon away from the double bond. And the reason why allylic carbocations are relatively stable is due to the resonance stabilization of the carbocation. This double bond can move here, creating a resonance form that looks like this. So as you can see, the plus charge is shared between 2 carbon atoms as opposed to 1. And as a result, it's more stable. So those are the main things you need to look for. So keep in mind that tertiary carbocations are more stable than secondary and primary ones, and that allylic carbocations are more stable than those that are not allylic. Now, let's identify the type of carbocation that we have in every choice. So let's start with part A. What type of carbocation do we have? So let's focus on the carbon with the plus charge. How many other carbons are attached to it? So we have 1, 2, 3. Because there are 3 carbons attached to it, it is a tertiary carbon. And notice that it's 1 carbon away from a double bond, which means it's tertiary and it's allylic. Now what about B? What type of carbocation do we have? So focusing on the carbon with the plus charge, that carbon is attached to 2 other carbon atoms and is adjacent to a double bond, which means that it's secondary and it's allylic. So moving on to part C, the carbon with the plus charge is adjacent to two other carbons, but it's too far away from the double bond, so it's simply a secondary carbocation. And now this carbon with the plus charge is only attached to one carbon atom, which means it's a primary carbon, and it's too far away from the double bond, so it's not allylic. So therefore D is the least stable. Primary carbocations are not stable at all. The most stable is answer choice A. It's tertiary and it's allylic. So if we had to rank it, compound A is the most stable. After that, the next most stable is B. A secondary allylic carbocation is more stable than a regular secondary carbocation due to resonance. And then B is more stable than C, and D is the least stable. But answer choice A is the answer. That's the most stable carbocation that we have in this selection. Number 4. Identify the hybridization of the indicated atoms shown below from left to right. So is it A, B, C, or D? How can we determine the hybridization? So feel free to try this one. Now before we work on the solution, let's review how to find the hybridization of an atom. So let's start with methane, CH4. So what you want to do is count the number of groups and lone pairs attached to the carbon. Single bonds, double bonds, triple bonds, count them as one group. So 1, 2, 3, 4. The carbon atom has 4 groups. 4 groups correlates to sp3. S1p3. 1 plus 3 adds up to 4. So that's the hybridization on the center carbon atom. So let's do some more examples so you can get familiar with this. Next, let's try formaldehyde, since it has a double bond. Now, how many groups are attached to the carbon atom? 1, 2, 3. Treat the double bond as one group, don't count it as 2. So we have 3 groups, which corresponds to sp2. 1 plus 2 adds up to 3. 3 groups will always correspond to sp2. 4 groups will always correspond to sp3. That's a quick and simple way to find the right answer. Now let's try acetylene. What is the hybridization at the carbon and at the hydrogen? So if we focus on the carbon atom, that carbon atom is attached to a hydrogen and a CH group. So it has 2 groups, which means that it's sp hybridized. 2 is basically 1 plus 1. If you don't see an exponent, it's 1. Now what about the hybridization on hydrogen? Hydrogen is only attached to one atom, so it only has one group. One group correlates to S. Now what if there are lone pairs? Let's use ammonia as an example. NH3. What's the hybridization on the nitrogen atom? So what we need to do is count the number of groups and lone pairs. So nitrogen has 3 atoms and a lone pair, so it has 4 groups. And 4 correlates to sp3. 1 plus 3 adds up to 4. Next, let's use sulfur dioxide as an example. So here's the Lewis structure of SO2. What's the hybridization on the sulfur atom? So sulfur has 2 groups and a lone pair. So it has a total of 3 groups, which is sp2. So it's sp2 hybridized. Now what if we have more than 4 groups? Let's use phosphorus pentachloride, for example. What's the hybridization on a central phosphorus atom? So here we have a total of 5 groups. So it's going to be S1, P3, D1. S only has 1 orbital, so there's no S2. P only has 3 orbitals, so you shouldn't have P4. D has 5 orbitals, so we don't have to use all 5. The exponents have to add up to 5. 1 plus 3 plus 1 is 5. So therefore, what do you think the hybridization will be for sulfur hexafluoride? SF6. So sulfur has 6 groups in this case. So 6 corresponds to S1P3D2. 1 plus 3 plus 2 is 6. So now that you know how to find the hybridization of an atom, go ahead and finish this problem. So let's start with CH3. So we have a carbon attached to 3 hydrogens, and it's attached to the carbon at the right. So let's put C here. So this carbon has 4 groups attached to it, which means that it's sp3 hybridized. So let's put sp3 here. Now we need to go in order from left to right. So in each answer choice, the first answer should be sp3. We can eliminate A, which is sp2. So we're between B, C, and D. Now let's move on to carbon number 2. So that carbon, we can see, has 3 groups. It's attached to the CH3 on the left, the CH2 on the right, and the oxygen. 3 groups correlates to sp2. 1 plus 2 is 3. So that's the second answer. It's sp2. So we can keep B, C, and D the same. As you can see, the second answer, they're all sp2, so we can't eliminate anything at this point. Now let's move on to carbon number 3. So we have a carbon that has 2 hydrogens, so we can draw it like this. And then to the right we have another carbon, and to the left we have another carbon. So the carbon, the CH2 carbon, has 4 different groups, and as we know, 4 correlates to sp3. We can eliminate answer choice B because the third option is not sp3. We need to keep C, and we need to keep D. So looking at C and D, we can see that the next option is sp. What we need to focus on is the last one. But if you look at this carbon, you can see why it's sp hybridized. It's attached to a carbon and another carbon. So it has 2 groups, which correlates to sp. 1 plus 1 is 2. Now if we focus on the hydrogen, that hydrogen is only attached to 1 group. It's attached to 1 carbon atom, and 1 group correlates to S. So the hybridization for any hydrogen atoms is always S, because hydrogen cannot form 2 bonds. It can only form 1 bond, which means that C is the right answer. D doesn't have S as the last option, so this is it. Number 5. Which of the following Lewis structures contain a sulfur atom with a formal charge of +1? So go ahead and try this problem. The formula that I like to use is this one. The formal charge is equal to the number of valence electrons minus the number of bonds plus the number of dots in the structure. So let's start with answer choice A. Sulfur has 6 valence electrons. If you go to the periodic table, you'll find that sulfur is in group 6A of the periodic table, and typically elements in that group have 6 valence electrons. So all of the sulfur atoms in each of these molecules have 6 valence electrons as a free atom. Now in structure A, or in compound A, sulfur has 4 bonds. 1, 2, 3, 4. And it doesn't have any visible lone pairs, so it has 0 dots. 6 minus 4 is 2. So the formal charge on this sulfur atom is +2. So we can eliminate answer choice A. Now let's move on to B. Sulfur has 6 valence electrons. In B, it has 6 bonds. 2, 3, 4, 6. It doesn't have any lone pairs, so the number of dots is 0. 6 minus 6 is 0. So we can eliminate answer choice B. It's neutral in that molecule. Now let's move on to C. Sulfur has 6 valence electrons, and in this structure, sulfur has only 1 bond, but notice that it has 6 dots. 2, 4, 6. 1 plus 6 is 7, and 6 minus 7 is -1. Therefore, we can eliminate answer choice C. So D has to be the answer, but let's go ahead and use the formula to get the answer. Sulfur has 6 valence electrons. In this structure, it has 1 bond plus 2, so that's 3 bonds in total. And we can see that it has 2 dots, or 1 lone pair. 3 plus 2 is 5. 6 minus 5 is 1. And so that's the formal charge of sulfur in answer choice D. So D is the answer. That's what we're looking for. Number 6. Which of the following represents the best Lewis structure for the cyanide ion? Is it A, B, C, or D? So which answers can we eliminate? We're looking at answer choice D. Notice that nitrogen, which is a second row element, has more than 8 electrons. Every bond represents 2 electrons. So it has a triple bond, which equates to 6 electrons, and 2 lone pairs. So nitrogen has 10 electrons around it, which violates the octet rule. Elements in the second row like carbon, nitrogen, oxygen, fluorine, they cannot have more than 8 electrons. In the second row you have 2s2, 2p6. There is no 2d10. So second row elements can have at most 8 electrons. 2 plus 6 is 8. So we can eliminate D. Nitrogen violates the octet rule. Now in answer choice C, what's the issue here? Carbon has an incomplete octet. Notice that it doesn't have 8 electrons, it has 6. Now it's possible for an element to have 6. However, it's not stable, it's not the best Lewis structure. It has 2, 4, 6 electrons, so we can eliminate answer choice C. Answer choice A and B. Carbon and nitrogen both have 8 electrons, which means that their octet requirements are satisfied. Now what we need to look at is the formal charge. We need to find out which one is more stable. The compound that is most stable is the one with the minimum formal charge, where the formal charge is closest to 0. So let's start with B. Let's calculate the formal charge. We know it's equal to the number of valence electrons minus the bonds plus the dots. So starting with carbon, carbon has 4 valence electrons naturally. It's in group 4A of the periodic table. And in the structure, it has 2 bonds and it has 4 dots. 2 lone pairs corresponds to 4 dots. Every lone pair has 2 dots. So 2 plus 4 is 6, and 4 minus 6 is negative 2. So that is the formal charge of carbon in this structure. So let's go ahead and write that. Now what about the formal charge of nitrogen? Nitrogen naturally has 5 valence electrons. It's in group 5A of the periodic table. And in this structure it has 2 bonds, and it also has 4 dots. So 2 plus 4 is 6, 5 minus 6 is negative 1. Now let's go ahead and calculate the formal charge of carbon and nitrogen in the other compound. So starting with carbon, we can see that it has 3 bonds, 1 lone pair. So it has 3 bonds and 2 dots. 3 plus 2 is 5, 4 minus 5 is negative 1. Now what about nitrogen? Nitrogen has 5 valence electrons. It too has 3 bonds. It has a triple bond. And it has a lone pair, so 2 dots. 5 minus 5 is 0. So is it better to have a formal charge of negative 1 and 0, or negative 2 and negative 1? Negative 1 is closer to 0 than negative 2 is, so we can eliminate B. If you have a formal charge of negative 2, it's not good. It's not stable. Also, the total charge for cyanide has to add up to negative 1. If we add these charges, they add up to negative 1. If we add these 2 charges, they don't add to negative 1. So this is not the correct Lewis structure for cyanide. This is it. Number 7. Which of the following represents a pair of resonance structures? Do you think the answer might be A, B, C, or D? So what can we do in order to identify a pair of resonance structures. Is there a better way of figuring this out instead of drawing everything? It turns out that there is. A quick way to identify a pair of resonance structures is to identify the ones that are not resonance structures. If any atoms are moving from one spot to another spot, it's not a resonance structure. If you want to draw a resonance structure, only the electrons are free to move and not the atoms. So if we look at answer choice A, this represents a hydride shift. The hydrogen moved from the tertiary carbon to the secondary carbon. And when that happens, the plus charge is going to move from the secondary carbon to the tertiary carbon. So basically, they trade places. So because the hydrogen was moved, this is not a pair of resonance structures. Now looking at D, we could see that the location of the bromine atom and the hydrogen atom were reversed. So anytime you're moving around atoms, it will not be a resonance structure. So D can be eliminated. In fact, these are basically cis and trans isomers. This is the cis isomer, and this is the trans isomer. In the cis isomer, you have two groups facing one side, and in the trans isomer, the two groups are on the opposite sides. Now let's move on to part C. Notice that we have a keto-enol tautomerization going on here. A hydrogen was moved from this carbon onto the oxygen. Before there were 3 hydrogens, and now we only have 2. So hydrogen was transferred from one part of the molecule to the other part of the molecule, which means that these two do not represent a pair of resonance structures. The only answer is answer choice B. If you draw all the hydrogen atoms, notice that none of them were moved. We still have 6 hydrogen atoms, 3 on each carbon, and so no hydrogens were transferred. The only thing that moved were the electrons. 2 pi electrons in the double bond was transferred to the oxygen, as we can see here. And anytime you move electrons without moving atoms, you're going to generate a resonance structure. So answer choice B is the right answer. Number 8. Which of the following would best act as the Lewis base? So in this problem, we need to identify which ones are the Lewis acids and eliminate them. And then we can easily see which one's going to be the Lewis base. A Lewis base is a nucleophile. It's electron rich. It's full of electrons, which means that it has a lot of lone pairs and it may have a negative charge. A Lewis base can donate a pair of electrons. Lewis acids, on the other hand, are electrophiles. They're electron poor. They're deficient in electrons, and typically they may have a positive charge. But the most important thing you need to know is that they have the ability to accept a pair of electrons. So let's look at answer choice A. Is it a Lewis base or is it a Lewis acid? Can it accept a pair of electrons or will it donate a pair of electrons? If we draw the resonance structure, notice that the carbon atom will have a positive charge. The oxygen now has a negative charge. So therefore, the carbonyl group, which correlates to aldehydes and ketones, they're typically electrophilic. They tend to act as Lewis acids. Let's say if we take a Lewis base like hydroxide. Hydroxide can donate a pair of electrons to the carbon, which means that acetone and ketones and aldehydes are all electrophiles, which means they're Lewis acids. So we can eliminate answer choice A. Now what about answer choice B? Is it a Lewis acid or is it a Lewis base? Or is it neither? Let's find out. So the methyl radical has an unpaired electron. Since it doesn't have a pair of electrons, it cannot act as Lewis base. For anything to act as a Lewis base, it has to donate a pair of electrons, which means 2 electrons. The radical only has 1 unpaired electron, so it can't donate 2 electrons. It doesn't have it. Now, can the methyl radical accept a pair of electrons? So let's say if we react it with hydroxide. Can hydroxide donate a pair of electrons to it, forming a bond? Let's say if it did. This bond will be created, and the oxygen, which had 3 lone pairs, now has 2. The carbon still have the 3 hydrogens, and it should still contain the radical, or this unpaired electron. Notice that this structure is not possible. Carbon cannot have 4 bonds and at the same time have an unpaired electron. That would violate the octet rule, and it's not possible. Carbon cannot have 9 electrons, which means that a radical cannot behave as a Lewis acid, nor can it behave as a Lewis base, particularly this particular radical. Now what about BH3? Is that a Lewis acid or is it a Lewis base? So we can see that boron doesn't have a lone pair, so it can't act as a Lewis base. It can't donate a pair of electrons. However, it can act as a Lewis acid. It can accept a pair of electrons from hydroxide. And then what's going to happen is we're going to get this product. So in this example, hydroxide, which donated the pair of electrons, is the Lewis base, or the nucleophile. BH3, which accepted the pair of electrons, is the Lewis acid, also known as the electrophile. So by default, the answer has to be water. And if we draw water, water has a lone pair. We can draw it like this. It has 2 lone pairs actually. And let's react it with BH3. So like hydroxide, water can use one of its lone pairs and donate it towards the boron atom. And so we're going to get a product that looks like this. Boron is going to have a negative formal charge. Oxygen is going to have a positive formal charge. And so we can clearly see that water is behaving as the Lewis base, which is the nucleophile. So D is the right answer. Number 9. Which compound is the strongest acid? So let's look at each answer choice. So for answer choice A, we have a carboxylic acid. You can see the functional group COOH. And what you want to do is you want to be able to determine the pKa of each of these molecules. If you know the pKa, you can tell which one's the strongest acid. As the pKa decreases, the strength of the acid increases. So the one with the lowest pKa is going to be the strongest acid. Carboxylic acids have a pKa of about 4 to 5. Now answer choice B, we have an alcohol, which most alcohols have a pKa roughly between 16 and 18. In the case of ethanol, ethanol has a pKa of 15.9. Answer choice C represents phenol. It has 6 carbons, 5 hydrogens, and an OH group. Whenever you see C6H5, it's a benzene ring attached to something else. Every carbon atom in a benzene ring has 5 hydrogen atoms. So C6H5 represents phenol. And phenol has a pKa of about 10. Next we have methylamine. Most amines have a pKa roughly of about 35 to 40. And E is a sulfonic acid. Whenever you see an SO3H group, these acids are very strong. This particular acid has a pKa of about -2. So the right answer is answer choice E. But now let's talk about it. Let's go over a few things. So how can we find out the answer if we don't know the pKa values? The first thing you want to compare is the element attached to the hydrogen atom. In our examples, is either an OH group or an NH2 group. The carboxylic acid has an OH group. The ethanol molecule and phenol has an OH group. Even a sulfonic acid has an OH group. The only one that's different is the NH2. So whenever you have a different element attached to a hydrogen, you can use the trend found in a periodic table. Acid strength increases as you go to the right due to increase in electronegativity, and as you go down due to increase in size. So what this means is that HI is more acidic than HBr, which is more acidic than HCl, and that's more acidic than HF. HF is more acidic than water, and water is more acidic than NH3, which is more acidic than CH4. But let's focus on this. Water contains an OH bond. NH3 has an NH bond. So the OH bond is more acidic than the NH bond if everything else is equal, assuming that they have the same charge. If one is positive and one is neutral, you can't use this comparison. Either they both have to be neutral, or they both have to have a negative charge, or both be positively charged. So the OH group is more acidic than the NH group, which means that D cannot be the strongest acid. So that's how you can eliminate D without knowing the pK values. Now let's look at B and C, because both of them contain an OH group. So ethanol has a pKa of 15.9, and phenol has a pKa of 10. And they both have an OH group attached to a carbon. So why is phenol much more acidic than ethanol? The answer has to do with the stabilization of the conjugate base. The more stable the conjugate base is, the more acidic the conjugate acid will be. So that's the conjugate base of phenol, also known as ethoxide. And this is going to be the conjugate base of phenol, which is phenoxide. So the conjugate base of ethanol is ethoxide, in case I said that incorrectly. And the conjugate base of phenol is phenoxide. So notice that the negative charge on phenoxide is not localized, it's delocalized. It can move around. We can draw a resonance structure, take a lone pair, form a double bond, and push the negative charge here. Because the negative charge can move about the ring, the conjugate base is more stable. And when you have a more stable conjugate base, you're going to have a stronger conjugate acid. So the negative charge is shared between the oxygen atom and 3 other carbon atoms. The negative charge can jump every 2 carbon atoms, so it can move to these other positions indicated in red. So that's why phenol is more acidic than ethanol. It's due to the resonance stabilization of the conjugate base. So we can eliminate answer choice B, since C is more acidic than B. Now let's compare A with C. So let's start with the conjugate base of phenol. Let's redraw it. And if we draw the resonance structure, we know that this electron, or those pair of electrons, can move here, pushing a negative charge on the carbon atom. And that will give us this particular resonance form. And we can draw 2 other resonance forms. So this lone pair can move here and push the other 2 electrons on the next adjacent carbon. So now the negative charge is in that position. So the negative charge is going to keep jumping 2 carbons away. So now we can draw another resonance form. So as you can see, the phenoxide ion has a total of 4 resonance forms. The negative charge can be placed on 1 oxygen atom or 3 carbon atoms. Now let's draw the conjugate base of acetic acid, which is known as acetate. And let's draw the resonance form. To draw the conjugate base, all you need to do is take off the hydrogen. Now this negative charge can move to the other oxygen atom, giving us these 2 resonance forms. So here's a question for you. Why is it that phenol is more acidic than acetic acid? I take that back. Why is it that acetic acid is more acidic than phenol when the phenoxide ion has more resonance structures? Because typically, the more resonance forms that you have would indicate a more stable conjugate base, which means a stronger acid, but we don't see that. Acetic acid is stronger, and it only has 2 resonance forms when we draw the conjugate base of acetic acid. So why is it that acetic acid is a stronger acid when it should be phenol, if we look at the number of resonance structures? So not only should you look at the number of resonance structures, but you should look at where the negative charge is being placed on what type of atom. Is it better to put a negative charge on an oxygen atom or on a carbon atom? Oxygen is more electronegative than carbon. Electronegativity increases towards the right. So it's a lot more stable to put a negative charge on an oxygen atom than a carbon atom. So if we look at the first resonance structure, the negative charge is placed on the oxygen atom. So let's assume that those 2 are equivalent. Now, in the second resonance form of the acetate ion, the negative charge is also on an oxygen atom. But in the remaining 3 forms of the phenoxide ion, the negative charge is on a carbon atom. It turns out that putting a negative charge on a single oxygen atom is more stable than putting a negative charge on 3 carbon atoms, because carbon really doesn't want to have a negative charge. Oxygen can stabilize it better. And so that's why acetic acid is more stable or more acidic than phenol, is because you have a negative charge on 2 oxygen atoms as opposed to 1 oxygen atom in the case of phenol. So putting a negative charge on a second oxygen atom increases the stability by a huge amount, as you can see based on the number. Acetic acid is much more acidic than phenol. Now this case is apparent if you compare answer choice A and answer choice E. So let me get rid of this stuff. So let's draw the conjugate base of methane sulfonic acid. Instead of drawing a methyl group, I'm just going to represent it with an R group. So we need to take off the hydrogen. Now if we draw the resonance form, we can take a lone pair and form a double bond, causing a negative charge to move on the other oxygen atom. So we can get this resonance form. And to get the next one, we can use a lone pair, form a double bond, breaking the other pi bond. So as you can see, because there's 3 oxygens, there's 3 different resonance forms that we can draw for the sulfonic acid. So the negative charge is shared between 3 oxygen atoms as opposed to 2 in the case of acetic acid. And we can see the pKa difference is significant. So that's why methane sulfonic acid is the most acidic one, is because first you're placing a negative charge on an atom that can stabilize it or that can take the negative charge, like oxygen. and the quantity of oxygen atoms. There's 3 resonance forms. That negative charge can be shared between 3 oxygen atoms as opposed to 2 in the case of acetic acid, or as opposed to 1 in the case of phenol. So the more resonance structures that you have, and if you can place it on an atom that can stabilize a negative charge, that will increase the stability of the conjugate base, making the conjugate acid more acidic. Number 10. What is the IUPAC name for the compound shown below? So take a minute and work on this problem. So what do you think we should do first? The first thing that I would recommend doing is converting the condensed structure into a line structure. So we have a CH3 and a CH2. That's 2 carbons right there once you draw a single line. And then we have a carbon double bonded to another carbon. And then we have a CH3 on the bottom, a CH2 on the top, and then a carbon which is attached to 3 methyl groups. And then let's draw the hydrogen as well. So that's the line structure. Now the next thing we need to do is identify the longest chain. So if we start from this end, this is going to be carbon 1, 2, 3, 4, 5, 6, 7. So it's going to be a heptane derivative as opposed to a hexane derivative, which means we can eliminate D. Hexene indicates that there's 6 carbon atoms in the longest chain, but we can see that there's 7. Now we need to know the right direction in which to count it. Should we count it from left to right or right to left? As we count it from right to left, notice that the double bond is between carbons 4 and 5. We need to give the double bond priority. Let's count it in the other direction. So let's say this is carbon 1, 2, 3, 4, 5, 6, and 7. Notice that if we count it from left to right, the double bond is now between 3 and 4 instead of 4 and 5, which is better. So now let's go ahead and name it. Notice that we have a methyl group on carbon 4, and we have 2 methyl groups attached to carbon 6. So it's 4, 6, 6 as opposed to 2, 2, 4. Now we're between A and B. Everything looks the same except one is E and the other is Z. So we need to know which isomer do we have. Is it E or is it Z? So we need to determine which group has more priority. So on the left side, is it the hydrogen or the ethyl group? The ethyl group has more priority than the hydrogen. Carbon has a higher atomic number than hydrogen. Now what about on the right side? Is it the methyl or is it these groups of carbons that we see here? If you have a chain of carbons, that's going to have more priority than a single carbon atom. If you analyze this, this is a methyl carbon compared to a secondary carbon. A secondary carbon has more priority than the methyl carbon. So the highest priority groups are on opposite sides. When they're on opposite sides, you have the E isomer. If they're on the same side, you have the Z isomer. So answer choice A is the right answer. Number 11. Which of the following molecules has the S configuration? A, B, C, or D? Well, let's find out. Let's start with A. So first, we need to rank each group based on their atomic numbers. Bromine has the highest atomic number, so we're going to give it a score value of 1. It has the highest priority. Next, fluorine has the second highest atomic number, and then it's carbon. So fluorine is going to be group number 2, carbon is 3, and H is number 4. So what you do is you count it from 1, 2, and 3. Ignore 4. So going in the direction starting from 1 to 2 to 3, notice that it's rotating in the clockwise direction, which is R. Now before you count it, you need to make sure that group number 4 is in the back, which it is. So A is not the answer we're looking for because it has the R configuration. So we can eliminate answer choice A. Now let's move on to B. So we can see that it's relatively easy to assign the configuration whenever H is in the back. You just simply have to count it in a direction starting from 1 to 2 to 3. Now what about when H is in the front? Well, let's do everything that we did. We know H is going to be number 4. Now, between these 3 groups, they all start with a carbon. But the CH3 doesn't have an oxygen, so this is going to be group number 3. Between these two, which one will have a higher priority? Well, the carboxylic acid has more oxygens than the alcohol. So therefore, that's going to be group number 1, and this is going to be group number 2. So what you need to do is count it in a direction from 1 to 2 to 3. But because H is in the front, you need to reverse it. As we go from 1 to 2 to 3, this is clockwise. That's R. But because H is in the front, and we want it to be in the back, we need to reverse it. So we get S, which means that C is the correct answer. So you always want group number 4 to be in the back. Now we know that B and D has to be R, but for the sake of practice, let's go ahead and work through those examples. Let's prove that it's R. Now in B, notice that group number 4 is not in the back. So what do you do in a situation like that? Well, let's find out. So we know hydrogen is going to be group number 4. But which one is group number 1? So notice that we have a carbon atom, and a sulfur. You need to compare the first atom that's attached to the center carbon atom before you look at the second atom. So you can't look at bromine yet. You have to focus on the CH2. Sulfur has a higher atomic number than both of these carbon atoms. So therefore, sulfur, or the SH group, is group number 1. It has the highest priority. Now, these two carbon atoms are similar, so let's move on to the second atom relative to the chiral carbon, and let's see if there's a difference. Bromine has a higher atomic number than oxygen. So therefore, this is going to be group number 2, and this will be group number 3. Now, there's a method that you can use if you don't have, let's say, like one of those ball and stick models. This is a method that I use to quickly determine if it's going to be R or S. If you have a group that's in the front or in the back, put it in a circle. So group number 2 is in the front, which means that we're going to have to reverse our answer to get the right answer when we assign R or S configuration. Now, at the top we have number 1. To the right of number 1 we have a 4. And to the left of number 1 we have the 3. So you want to put the 3 numbers similar in the form of a triangle around the number that's in a circle. Now, currently group number 1 is on top. We want to rotate the molecule such that group number 4 is on top. So let's rotate it counterclockwise. So now 4 is going to be on the top, 2 is still in a circle, and keep in mind, the stuff that's in a circle represents what's in front. Now 1 is going to be to the left, and 3 has moved to the right. Now what we're going to do is we're going to flip the molecule. We're going to flip it in such a way that number 4 is going to kick out number 2. So 4 is going to be in the front. 1 and 3 are going to flip in the upward direction. So 4 is in a circle, 2 has been kicked out, and 1 and 3 are at the top now. Now we can count it from 1 to 2 to 3. So right now, this appears to be S, counterclockwise. But because number 4 is in the front, we need to reverse it. So the answer is R, which means B is not an answer. Now what about the last one, D? The answer that we're looking for is S, and we know that C is the right answer. So let's prove that answer choice D has the R configuration. Feel free to try this method yourself. Go ahead and pause the video and try it. So first, let's identify the 4 groups that we have. We know the hydrogen is number 4. Now if we compare the carbon atoms with the oxygen, oxygen has a higher atomic number, so the OH group is number 1. Now comparing the methyl group and the aldehyde group, the aldehyde group has an oxygen, so it's going to beat the methyl group. So this is going to be number 2. The methyl group is number 3. So group number 3 is in the back. Let's put that in a circle. So for this one, we don't have to reverse it because what's inside the circle is already in the back. We want group number 4 to be in the back of the molecule. Right now, group number 1 is on top, so let's put that here. 4 is to the right of number 2, and 2 is to the left. So let's rotate the molecule counterclockwise. We want 4 to be on top, so we can kick out 3. So now we're going to flip the molecule such that 4 kicks out 3, and 1 and 2 are going to flip to the top. So it's going to be 1, 2, 4 in the center, 3 below. So keep in mind, what's in the circle represents what's in the back. So we just got to count it from 1, 2 to 3. So this is the R configuration. So therefore, only answer choice C has the S configuration. So answer choice C is the right answer. Number 12. Which reaction will generate a pair of enantiomers? What do you think the answer is going to be? Well, let's start with D. If we combine an alkene with osmium tetroxide and H2O2 or hydrogen peroxide, we're going to get 2 alcohol functional groups on the same side, basically with syn addition. Now we can get 2 in the front and we can get 2 in the back. So these 2 molecules, are they a pair of enantiomers or is it a single meso product? It turns out that these are the same. Notice the symmetry. Even if the chiral centers change configuration, if there's a line of symmetry, it will not be a pair of enantiomers. Instead, we have a meso product, which means these 2 compounds are identical. So therefore, D is eliminated. That's a meso product. Now what about answer choice C? Deuterium works the same way as hydrogen. Deuterium will add across a double bond, turning it into a single bond. And the reaction proceeds via syn addition, which means the 2 deuterium atoms will be on the same side. So therefore, this will generate a meso product as well. So you get a single product. So answer choice C is eliminated. Now let's move on to B. If we combine an alkene with a peroxy acid, it could be RCO3H. Another peroxy acid you might see is MCPBA. Basically, they do the same thing. If we put these 2 together, we're going to get an epoxide. Now the epoxide reaction works with syn addition, which means that it's on the same side. So we can write it like this. This is one way we can draw the product. We can also draw it like this as well. So as you can see, there is a line of symmetry. And so it can't be a pair of enantiomers if there's a line of symmetry. So this too generates a meso product. So B is eliminated, which means A has to be the answer. Bromine adds across the double bond via anti-addition. And so the products will look like this. Notice that all chiral centers have been reversed in the 2 products, and also that we do not have a line of symmetry. So if you look at it carefully, this side is the same as that side. And these 2 BRs are not the same. One is in the front and the other is in the back. Now you might be thinking, well, there's 2 carbons here, only 1 carbon here. But if you draw it like carefully, let's say if we draw it this way, the line of symmetry really exists here. So as you can see, these 2 carbons, they're symmetrical about each other. This is on the line of symmetry. And these 2 bromine atoms, because one is in the front and the other is in the back, they're not symmetrical. So that's why we don't have a line of symmetry in this case. And so A would represent a pair of enantiomers. Number 13. Which of the following Newman projections represents the most stable conformation of this molecule here? So go ahead and try this problem. The first thing we should do is we should draw a better structure. Let's expand the condensed structure. So let's start with the CH. So that carbon has a hydrogen and it has two CH3 groups attached to it. So it looks like this. Next, it's attached to another CH group. So basically that's a carbon with a hydrogen. And this CH is attached to a CH3 and is attached to a CH2 CH3 group. So that's the structure that we have. And looking at the answers, we can see that these two methyl groups corresponds to these two methyl groups. And this hydrogen also corresponds to it. So therefore, we're viewing it along the C2-C3 bond. So the C2 carbon is the one in the front. The C3 carbon is behind it. We can't see it. Now attached to the C3 carbon, we have, I'm going to highlight it in yellow, we have a CH3 group, we have a hydrogen, and we have an ethyl group. So now you know how to turn a condensed structure into a Newman projection. So looking at A, B, and C. A, B, and C have the right number of carbons. However, D does not. A, B, and C all have 3 methyl groups. Answer choice D only has 2 methyl groups. So therefore, D doesn't have the right number of carbons. We can eliminate answer choice D. Now let's just get rid of a few things. So we need to identify the most stable conformation of the Newman projection that represents this molecule along the C2-C3 bond. So how can we do this? We need to count the number of gauge interactions. This is a gauge interaction. The CH3 groups are 60 degrees apart. So we'll call this a methyl-methyl gauge interaction. This is another methyl-methyl gauge interaction. And that's a methyl-ethyl gauge interaction. So A has 3 gauge interactions. B also has 3 gauge interactions. Here we have a methyl-ethyl gauge interaction, another methyl-ethyl, and a methyl-methyl gauge interaction. Now looking at answer choice C, there's only 2 gauge interactions. A methyl-methyl gauge interaction and a gauge interaction between a methyl and an ethyl group. So because answer choice C has the least number of gauge interactions, and all of these are staggered conformations, answer choice C represents the most stable conformation. Now between A and B, which one is more stable? So the methyl-methyl gauge interactions are the same, so we can cancel one of them. And the methyl-ethyl gauge interactions are the same. Now B has an additional methyl-ethyl gauge interaction. A has an additional methyl-methyl gauge interaction. So which requires more energy? To put a methyl group next to an ethyl group or 2 methyl groups next to each other? Now the ethyl group is bulkier or bigger than the methyl group, so there's going to be more steric strain when a methyl interacts with an ethyl. So therefore, because it's more steric strain in answer choice B, it's going to be less stable than A. So if we had to rank it, C would be number 1. It's the most stable. Then A would be number 2. It's the second most stable. And B would be number 3. It's the least stable out of what's listed here due to the extra methyl-ethyl interaction. And we can't compare D because that represents a completely different compound. But C is the right answer for this problem. Number 14. Which is the most stable conformation of trans 1-fluoro 4-methyl cyclohexane? So first, let's identify which of these represents trans and which ones are cis isomers. So A, is it a trans isomer or a cis isomer? The fluorine is in the equatorial position, which is towards the side. But notice that it's going down slightly, so it's equatorial down. And the methyl group is in the equatorial position, but it's slanted slightly up. So if one position is up and the other is down, that is going to be the trans isomer. Now looking at answer choice B, the fluorine is in the axial up position. So I'm going to put U for up. The methyl group is in the axial down position. So that also represents a trans isomer. In answer choice C, the fluorine atom is in the equatorial down position, and the methyl is in the axial down position. So because they're both in the same direction, that is in the downward direction, this represents the cis isomer. Now for answer choice D, fluorine is in the up position, and methyl is in the equatorial up position. So they're in the same direction, so this also represents a cis isomer. So we can eliminate answer choice C and D. We're looking for the trans isomer. Now in answer choice A, both groups are in the equatorial position. In answer choice B, they're both in the axial position. Which one is more stable, axial or equatorial? Well, there's something called 1,3-diaxial strain. So let's say if we start from the fluorine. On the third carbon, you have a hydrogen. And if you count in the other direction, there's another one. Fluorine interacts with these hydrogen atoms, making the axial position less stable. So therefore, the most stable conformation is the one that has all the groups in the equatorial position. So answer choice A is the answer. Number 15. Which reaction will produce a racemic mixture of chiral products? So what do you think the answer is going to be? Well, let's go through each one. Once we add HBr to a double bond, or to an alkene, the double bond is going to turn into a single bond, and we just got to add the bromine atom. Now, this reaction typically occurs with more carbon-to-carbon stereochemistry. However, because the two carbon atoms across the double bond have the same substitution, they're both secondary carbons, this reaction is not regioselective. So you can put the bromine atom on any one of those two carbon atoms. So let's put it there. This particular product, is it chiral or achiral? The carbon that bears the bromine, does it have 4 different groups? It has a bromine atom, it has a hydrogen atom, but notice that the left side is equivalent to the right side, so it's not chiral. So that's an achiral product, which means we can eliminate answer choice A. Now what about B? Will B generate an achiral product? Well, this carbon is secondary, this one is tertiary. The bromine is going to go on the tertiary carbon. The reason for that is because tertiary carbocations are more stable. And we can go over the mechanism later. But for now, this is going to be the product. Now, this particular product, is it chiral or achiral? So analyzing the carbon that has the bromine atom, that carbon has a bromine atom, an ethyl group, but notice that it has 2 equivalent methyl groups. So it doesn't have 4 different groups, which means that it's achiral. So we can eliminate answer choice B. Now what about C? In this reaction, there's going to be a carbocation rearrangement. You're going to get the same product as answer choice B. So C is eliminated. The correct answer is D. But let's talk about why. We have one butene, and we're going to react it with hydrobromic acid. So in the mechanism, the first thing that's going to happen is the nucleophilic double bond is going to grab a hydrogen in HBr, expelling the bromine atom. Now initially, bromine has 3 lone pairs, but once the HBr bond breaks, bromine is going to pull the electrons toward itself. Bromine is more electronegative than hydrogen, and so when that bond breaks, that's why it pulls the electrons toward itself. Now, where is the hydrogen going to go? Should we add the hydrogen to, let's say, the primary carbon or the secondary carbon? The hydrogen is going to go on a primary carbon. If we put it there, we're going to get a more stable secondary carbocation. If we put the hydrogen on a secondary carbon, we're going to get a less stable primary carbocation, which we don't want that. So now, the bromide ion, which now has 4 lone pairs instead of 3, and it has a negative charge, it's attracted to the carbocation. And so it could approach it from the front or the back. And that's why we can get a racemic mixture of products. So if it approaches it from the front, we can get this product. Or if it approaches it from the back, we can get this product. And both of these compounds are chiral. So if we analyze this carbon, it has a CH3 group, it has a bromine, it has a hydrogen, and it has an ethyl group. So we have a racemic mixture of chiral products. Now granted, this may not be a 50-50 equal racemic mixture. It could be 40-60, 55-45, but we do have both enantiomers though. Now what about the other reaction in part C? We mentioned that we're going to go over it. Let's talk about the mechanism. So just like in the previous reaction, the double bond is going to react with HBr. It's going to acquire the hydrogen. And just like before, we're going to put the hydrogen on the less substituted carbon, that is the primary carbon, so we can get a more stable secondary carbocation. Now the secondary carbocation is adjacent to a tertiary carbon. Whenever you see that, there's going to be a hydride shift. And so this hydrogen is going to glide towards that carbocation. And so the hydrogen and the carbocation, they're going to trade places. So now the plus charge is on the tertiary carbon. And the bromide ion can attack from the front or the back, but it doesn't matter because that carbon is not chiral due to the methyl groups. So because that carbon has 2 methyl groups, it doesn't have 4 different groups. So therefore this product is achiral. And based on this mechanism, you can write out the mechanisms for answer choice A and B. There's no carbocation rearrangement for those. So the first step is going to be the same. You just add HBr, and then the bromide attacks the carbocation, and you'll get the product. So that's it for this problem. 16. Which radical is most stable? Is it going to be A, B, C, or D? Well, let's identify each radical. So let's start with A. This carbon is secondary because it's attached to 2 other carbons, and it's adjacent to a double bond. So this is a secondary allylic radical. Now looking at answer choice B, this carbon is also secondary, and it's next to, it's 1 carbon away from a benzene ring. So this is a secondary benzylic radical. Here we have an arrow radical. The unpaired electron is directly attached to a double bond. And for answer choice C, we have a tertiary benzylic radical. And the reason why it's tertiary is because the carbon that bears the radical is attached to 3 other carbons. and it's 1 carbon away from the benzene ring. So which of these is most stable? Well, it turns out that the tertiary benzylic radical is the most stable. 1. Tertiary radicals are more stable than secondary radicals. By the way, this is a secondary aryl radical. The radical is attached to 2 other carbon atoms. So we have the most substituted radical in answer choice C, but also notice that it's attached to 3 benzene rings. So there's a total of 10 resonance structures that you can draw. There's 9 additional structures, including, well, if you add this one, then it's a total of 10. But not including this one, there's 9 other resonance structures that you can draw. This compound only has a total of 4 resonance structures. A only has a total of 2 resonance structures. D doesn't have any. D is the least stable. It's not good to put a radical directly attached to a double bond or directly on a benzene ring. So if we had to rank it, C is number 1. It's the most stable. The second most stable, would you think it's A or B? The second most stable is going to be B. The secondary benzylic radical, as we mentioned before, it can form 4 resonance structures, including the one that you see here. Whereas in A, we can only get 2 resonance structures. So therefore, B is going to be the second most stable, A is the third most stable, and D is the least. Now let's talk about the resonance structures that we can draw. Let's start with the secondary allylic radical. Now when dealing with radical compounds, you need to use half arrows. Half arrows represent the flow of 1 electron, and a full arrow represents the flow of 2 electrons. So the double bond basically has 2 electrons on it. So we can represent it like this. One of the electrons will move to form a double bond, and the other unpaired electron will move in this direction. The other one will stay where it is. So we're going to get this particular resonance form. And there's going to be a radical left on the primary carbon. Which of these 2 resonance contributors is more stable? Which one contributes more to the resonance hybrid? The one that's more stable is the secondary radical. Secondary radicals are more stable than primary radicals. So if you ever get a question to ask you which one is the major resonance contributor, it's simply the resonance form that's more stable. Now let's say if you're going to draw the resonance structure from this form instead of using 2 dots here. Here's what you need to do. There's going to be 3 arrows that you need to show instead of 2. So the first arrow and the second arrow is going to be the same. However, you need to show this third arrow where the radical is going to be placed on the primary carbon. And this would lead us to get this product. Now going back to this compound, let's show all 4 resonance structures. Feel free to pause the video and try it yourself. So first, we can break this double bond and put a radical 2 carbons away from the first one. So the radical is over here. Next is going to jump 2 carbons away to the next position. So 1 electron will move over here, and this radical, or that unpaired electron, will combine with it to form a double bond, and the other unpaired electron will form a radical 2 carbons away. So now we have a double bond here, and this is a tertiary radical. Now for the last one, we can follow the same process. So this is the 4th resonance structure that we can draw. And so that's it. So now you know how to draw the different resonance forms when dealing with radicals and double bonds. Number 17. Which proton is most acidic? Well, let's find the pKa values. And whichever hydrogen has the lowest pKa value, that's going to be the one that's most acidic. So what is the pKa of a hydrogen that's attached to, let's say, an alkyne? The pKa is about 25. For a hydrogen that is basically part of an alkane carbon, the pKa is very high. It's about 50 to 60. A hydrogen that's attached to an alkene, the pKa is around 44, if I remember correctly. It's somewhere in the 40s. And for an alcohol, the pKa is about 16 to 18. So clearly we can see that the OH group is going to be the most acidic. It has the lowest pKa value. So D is the answer. So if we had to rank it, this is the most acidic. The second most acidic is the hydrogen that's attached to the alkyne. This is the third most acidic, and this is the least. And so that's it for this problem. Number 18. Which halide will react most rapidly with a hydroxide ion in an SN2 reaction? Is it A, B, C, or D? Well, the first thing that we should do is we need to convert the condensed structure into a line structure. So let's start with A. We have a carbon that's attached to 3 methyl groups, and we have a bromine atom on it. So basically, this is a tertiary alkyl halides. It turns out that tertiary alkyl halides do not work very well in an SN2 reaction. And the reason for that is due to steric hindrance. The hydroxide, which is the nucleophile, is going to have a difficult time approaching the carbon that it needs to attack. And the reason for that is because these bulky methyl groups, they block approach to the carbon that it has to attack. So those methyl groups block that carbon, they protect them from nucleophilic attack. And so that's why tertiary alkyl halides do not work very well for SN2 reactions. So A is eliminated. Now looking at answer choice B, this is 1-bromobutane. So we have 4 carbons and a bromine atom. That's a primary alkyl halide. Primary alkyl halides work pretty well for SN2 reactions. Methyl halides work better than primary halides because the methyl carbon is very accessible to the nucleophile. Primary halides work better than secondary ones, and secondary halides are more accessible than tertiary ones. Answer choice C has 3 carbons and a bromine atom, but answer choice C represents a primary allylic halide, and answer choice D represents a vinylic halide. The bromine is attached to a carbon that is part of the double bond system. Now, something else that you need to know is that vinylic halides do not work at all for SN2 reactions and for SN1 reactions. So therefore, we could eliminate answer choice D. So we're between B and C. So which is better, a primary alkyl halide or a primary allylic halide? It turns out that allylic halides are more reactive toward SN1 and SN2 reactions than their alkyl halide counterparts. So a primary allylic halide works better than a primary alkyl halide. So C is a better substrate than B. It's going to react more rapidly in the SN2 reaction. So this is the answer. 19. What is the major product that results when R2-bromobutane reacts with sodium iodide and acetone? So first, let's draw R2-bromobutane. We need to put the bromine atom in the front, and we need to put the hydrogen in the back. So let's make sure it's R. The bromine atom has the highest priority. Next is the ethyl group, then the methyl group. So if we count it from 1, 2 to 3, H is in the back, which is group number 4. We can see that we have the R isomer. Now we're going to react this with sodium iodide and acetone. So what kind of reaction will we have? Is this an SN2 reaction? Is it an SN1? Typically, when you have an alkyl halide reacting with some sort of nucleophile, you have to think about nucleophilic reactions and elimination reactions. This particular reaction is an SN2 reaction. We have the secondary alkyl halide, and sodium iodide, the iodide part, is a good nucleophile, and acetone is a polar aprotic solvent. Aprotic solvents do not have any OH or NH groups, and they work well for SN2 reactions. So what kind of product will we get? In the SN2 reaction, the iodide is going to attack the substrate. It's going to act as a nucleophile. It's going to attack the carbon from the back, expelling the bromine atom. Because it approaches it from the backside, we're going to have inversion of configuration. So the iodide is going to be in the back, and now H is in the front. So before we had the R isomer, now we have the S isomer. So the product is 2-iodobutane, but the S isomer. So B is the answer. The only way we can get a mixture is if it was an SN1 reaction. Then D would be correct. But this is an SN2 reaction, which doesn't yield a racemic mixture. It only gives you the inverted product. So SN2 reactions always occur with inversion of configuration. So B is the answer. Number 20. Which reagent will produce the product shown below? So how can we convert 3-methyl-1-butene into 3-methyl-2-butanol? Well, let's start with answer choice A. Water with H plus is equivalent to H3O+. This reaction will give us an alcohol, but rearrangements will occur. It turns out that the OH group will be on the tertiary carbon, which is not what we want. So answer choice A is not the right answer. Now let's focus on answer choice B. Hydroboration followed by oxidation. This reaction occurs with Markovnikov anti-regiochemistry, or just anti-Markovnikov regiochemistry. You know what I mean. In this case, the OH group will be on the less substituted carbon atom of the double bond. So it's going to go on a primary carbon as opposed to the secondary one. So B won't give us the answer that we want. Now, answer choice C. We have MCPBA, metachloroperoxybenzoic acid. Once we add that, we're going to get an epoxide, which will look like this. And then once we add H3O+, the ring will open, giving us 2 alcohols, which we don't want 2 alcohols, we want 1. We don't want a diol. So C is eliminated. The only one that will give us the Markovnikov product without rearrangement is mercury acetate with water followed by sodium borohydride. So D is the right answer. Now let's go over a few things, particularly the mechanism of some of these reactions. So let's react this alkene with H3O+. So the first thing that's going to happen, the double bond is going to grab a hydrogen, expelling water. Now we're going to add the hydrogen on the less substituted carbon of the double bond. That is on a primary carbon. If we do that, we're going to get a secondary carbocation. Now the secondary carbocation is adjacent to a tertiary carbon, which means that a hydride shift will occur. And so now what we have is a tertiary carbocation, and at this point, water is going to react with it. So now oxygen now has the positive charge. Anytime oxygen has 3 bonds, it's going to have a plus charge. Now what we need to do is use another water molecule to get rid of one of these hydrogen atoms. So the final answer is this particular alcohol, 2-methyl-2-butanol. So as we can see, A is not the right answer. It's not the product that we want. So now let's move on to B. So once we add boron, I'm going to write it like this. Once we add BH3, it's going to react with the alkene, forming this product. The hydrogen is going to go on a more substituted carbon, since hydrogen is more electronegative than boron, and the BH2 group will go on the less substituted carbon. Now, once we add sodium hydroxide with hydrogen peroxide, the net result is that the BH2 group will be replaced with an OH group. And so, this is the product for that reaction. Now let's talk about the reaction in part C, or answer choice C. So first, we're going to react it with a peroxy acid, RCO3H or MCPBA. This will give us an epoxide. Now once we add H3O plus to it, which I'm going to write it out, the oxygen is going to receive a hydrogen from H3O plus. So it's going to be activated. And once H3O plus loses a hydrogen, it converts into water. Now water is going to attack the secondary carbon as opposed to the primary carbon. It turns out that the secondary carbon has more partial charge than the primary carbon, and so that's why water is attracted to it. If you draw the resonance structure of this molecule, which bond should we break? This one or this one? If we break this bond, this will give us a primary carbocation, which is not stable. However, let's say if we break the other bond, this will lead to a more stable resonance structure, which is a secondary carbocation. Now the resonance hybrid is somewhere in between these two structures. So because this carbon has a positive charge in one of the resonance forms, then this one has to have significant partial positive charge, which means water is attracted to that carbon. So it's going to attack the secondary carbon and not the primary one. So we're going to have an OH group on this carbon and a water on the other one. So now all we need to do is use another water molecule to get rid of one of the hydrogens. And so now we have a diol, which occurs with anti-addition. But that's not the product that we're looking for. Now let's focus on the oxymercuration demercuration reaction. So the alkene will react with mercury acetate. The mercury atom has a lone pair. So the double bond is going to attack the mercury atom, causing one of the acetate groups to be expelled, and the lone pair on the mercury atom will simultaneously react with the double bond. So we're going to get this cyclic mercurinium ion, which looks like this. At this point, mercury has a positive charge. The acetate that was kicked out has a negative charge. Now this carbon, just like before, in the other example, has a significant amount of partial positive charge. So the water that's in the reaction will be attracted to it. So it's going to attack from this side, causing this bond to break. And so the mercury atom is going to be on the primary carbon. On the secondary carbon, we have an oxygen. Now we need to remove the hydrogen. We can use water, or better yet, we can use acetate, which is a weak base. So now we have this intermediate. And in the last step, we need to add sodium borohydride. Now the mechanism for this step is not precisely known, but we do know the end result. The end result is that the mercury group will be replaced with a hydrogen. Now, since we don't have to show the hydrogen, we could simply write the final product like this. It's 2-methyl, or rather 3-methyl 2-butanol. And so that's it. Number 21. What is the major product of the reaction shown below? So we have a cycloalkene and a hydroboration oxidation reaction. What do you think the major product is going to be? Well, first, let's look at the regiochemistry. We have a secondary carbon and a tertiary carbon that are part of the double bond system. Now, the hydroboration oxidation reaction is an anti-Markovnikov reaction, which means that the alcohol, the OH group, should be on the less substituted carbon, that is the secondary carbon, since it's an anti-Markovnikov addition reaction. So therefore, C and D will not be the answer. We can eliminate those two. So now let's move on from the regiochemistry and let's analyze the stereochemistry of the reaction. In answer choice A, the methyl group and the alcohol group, they're cis with respect to each other. Here, it's trans. Which one will be the right answer? So what we need to know is that the hydroboration oxidation reaction occurs with syn addition. Now the syn addition, it doesn't have to do with the methyl group because the methyl group was already present in the reaction. The syn addition is between the hydrogen and the OH. So in both cases, the methyl group is in the front. So let's rewrite that. Now we need to put the OH group on the secondary carbon and the hydrogen on the tertiary carbon. So the hydrogen has to be on the back. I'm going to put it in red. We're adding the hydrogen to it. And because the OH group and the hydrogen has to be syn with respect to each other, meaning they have to be on the same side, the OH group has to be in the back. So this reaction is syn addition with respect to the hydrogen and the OH group that are added across the double bond. But it's trans if you compare the OH group and the methyl group. So therefore, the correct answer is answer choice B. So the reaction is syn addition, but it's syn with respect to the H and the OH. It appears to be trans because you don't look at, the hydrogen's not visible here. If you're just looking at the CH3 and the OH, it will be trans, but with respect to the hydrogen and the OH, those two groups should be on the same side. So B is the right answer for this problem. Number 22. What is the major product from the reaction of propene with bromine and water? So propene has 3 carbons and a double bond. And so we're going to react it with Br2 and H2O. Whenever you react an alkene with bromine and water, you're going to get 2 functional groups. You're going to get a bromine atom and you're going to get an OH group. So we can eliminate answer choice D. We're not going to get 2 alcohol groups and we're not going to get 2 bromine atoms. So we're either between A or C. Now it turns out that the more electronegative atom goes in the more substituted carbon, which is the OH group. So the OH group is going to go on the secondary carbon and the bromine is going to go on the primary carbon. So the correct answer is answer choice C. But let's write up a mechanism for this reaction. So the first thing that happens is that the alkene reacts with bromine. So the double bond is going to attack one of the bromine atoms, expelling the other, and at the same time bromine attacks the double bond. So initially bromine has 3 lone pairs, and the bromine that gets attacked is going to use up one of its lone pairs. It's going to form a cyclic intermediate, so it's going to have 2 lone pairs left over, and it's going to have a positive charge. The other bromine atom leaves as bromide, and it's going to have 4 lone pairs and a negative charge. Now we have water in the solution, and because the reaction is dissolved in water, there's a lot more water molecules than bromide ions. So water is going to attack the carbon. Now keep in mind, there's considerable partial positive charge on the secondary carbon. And water, it has an oxygen with a partial negative charge. That oxygen is attracted to this partially positive carbon atom. It's going to attack it from the back, expelling the bromine atom to the other side. And so that's why the oxygen is on the secondary carbon and the bromine is on the primary carbon. It's because of the backside attack. Now the oxygen has a positive charge. There's one more step in this reaction. We need to use another water molecule to get rid of this hydrogen. And so this is going to be the product. It's 1-bromo, 2-propanol. Number 23. Which of the following represents a free radical termination step? Is it going to be A, B, C, or D? So here are some things that you need to know. Let's say if you have a reaction, A plus B turns into C plus D. Anytime you have 2 radicals, one on each side, this is going to be a propagation step if you have a radical on the left and on the right side. Now let's say if you have 2 radicals on the left side, this is going to be a termination step. And if you have 2 radicals on the right side as opposed to the left side, this is an initiation step. And that's a quick and simple technique to distinguish initiation from propagation and from termination. So we're looking for a termination step. So we're looking for the reaction that has 2 radicals on the left side. So answer choice B fits that description. So B is the answer. B is a termination step. Now looking at answer choice A, is it initiation or propagation? Because there's a radical on the left and on the right side, it's a propagation step. The same is true for C. Looking at answer choice D, we have 2 radicals on the right side. So that's an initiation step. And so that's it for this problem. Number 24. What is the major product of the reaction shown below? Is it A, B, C, or D? Now, what you need to know for this type of problem is that when you mix bromine with HV, either UV light or even heat, it's going to be a radical reaction. And whenever you have a halogen reacting with an alkane, this is an alkane, under radical conditions, the bromine is going to replace the most substituted hydrogen. So if you have a primary hydrogen, a secondary hydrogen, and a tertiary hydrogen, it's going to replace the tertiary hydrogen. Now we do have a tertiary carbon. This carbon is tertiary, which means the hydrogen attached to it is tertiary. So bromine is very selective. It's going to go for the tertiary hydrogen. Now if we had chlorine, chlorine is non-selective. It's going to go for any hydrogen that it can get its hand on. It's very reactive. Bromine is less reactive, more selective. So it's going to replace the tertiary hydrogen, which means that C is the right answer. Now let's go over the mechanism of that reaction. So the first thing that happens once we add UV light, the bromine molecule is going to split into 2 parts. Once it gains enough energy, each bromine atom is going to take one electron and the two electrons in that bond. So we're going to get two bromine radicals. Once we generate the bromine radical in that initiation step, the next step is going to be a propagation step. The bromine radical is going to react with the tertiary hydrogen. So there's two electrons in this bond. One of those electrons will be used to form the bond between H and Br. So that's going to be a side product. The other electron, it's going to stay on the tertiary carbon. So we're going to get a tertiary radical. Now this radical, we can react it with another bromine molecule, since we have plenty of them in the reaction. So one of the electrons in the bond between the two bromine atoms will react with the radical, giving us the product. The other bromine atom is going to take the other electron with it, regenerating the bromine radical. So that is a propagation step, since we have one radical on the left and one on the right. Alternatively, we can get the same product using a termination step. So we could start with the tertiary radical and react it with a bromine radical. So these two would simply combine. And keep in mind, when dealing with radical reactions, typically you're going to be using half arrows, which represents the flow of one electron. A full arrow represents the flow of two electrons. And so those are the different ways that you can get the product. You can get it through a propagation step or even a termination step. The propagation step is more likely because there's a lot more bromine molecules than bromine radicals. The amount of bromine radicals in a solution is very small. So this step will occur more frequently. 25. What is the major product of the reaction shown below? NBS with heat or light works the same way as Br2 with HV. NBS produces radical bromine very slowly when activated with heat or light. So we know that the radical bromine is going to replace a hydrogen that will lead to the most stable radical. In the last example, the reason why it went for the tertiary hydrogen is because of the stability of a tertiary radical. A tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. So what we need to do is figure out which radical is more stable. Looking at answer choice A, the bromine is on this carbon. So let's say if we take away the bromine atom and just simply put a radical there. Will that radical be the most stable radical? If we take away bromine, that's going to be a primary radical. Here, if we take away the bromine, it's a vinylic radical. Vinylic radicals are not stable, so we can eliminate answer choice B. Now, if we put it here, this is going to be a primary radical, but because it's one carbon away from the benzene ring, it's a benzylic radical, which means that it's stabilized by resonance. So C is a good answer, but if you look at D, it's a secondary radical, and because it's one carbon away from the benzene ring, it's also benzylic. It turns out that you can get a mixture of C and D. However, the question wants the major product of the reaction. Because the secondary benzylic radical is more stable than a primary benzylic radical, D is going to be the answer. The major product is D. The minor product is C. You won't get A or B, and if you do get it, it's going to be very, 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 very low. But D is the answer. Number 26. Which acid has the lowest pKa? Is it going to be A, B, C, or D? So how can we find the answer? Well, we can use the trend on a periodic table. As you travel from left to right, acidity increases due to increase in electronegativity. So an OH group is always more acidic than an NH2 group. Keep in mind the typical pKa of an alcohol is 16 to 18, and for an amine, it can be anywhere from 35 to 40. So we're looking for the one with the lowest pKa. We're looking for the strongest acid. Now, which one is more acidic? An amine or a protonated amine? Anytime you add a hydrogen to something, the one with the positive charge is going to be more acidic than a neutral one. A protonated amine has a pKa of about 9 to 10. As you can see, this is much lower than this one. So we can eliminate answer choice B. And the protonated amine is more acidic than the alcohol, so we can get rid of A. Now the protonated alcohol is even more acidic. If OH is more acidic than NH2, then OH plus 2 must be more acidic than NH3 plus. So clearly, the correct answer is C. A protonated alcohol has a pKa somewhere in the negative range. It could be like -2 or -3, but it's very acidic. So this is the answer. Number 27. What is the IUPAC name of the molecule shown below? So first, let's identify the longest chain. So this is going to be carbon 1, 2, 3, 4, 5. We want to count it in that direction so we can get a 2-bromo and the alcohol on 3. If we count it the other direction, we're still going to get the OH on 3, but the bromine will be on 4. And you want to count it in such a way to get the lowest numbers. So we want to count it from the top to the bottom. So there's 5 carbons, and the functional group is an alcohol, so it's pentanol, which means that we can eliminate answer choice D. So everything else is the same, 2-bromo, 3-pentanol. The only thing that's different is the configuration. So we need to determine if we have an R or an S isomer. So let's start with this chiral center, carbon number 2. Now we know that the hydrogen is group number 4. It has the lowest priority. Bromine has the highest. This entire group here is going to be group number 2. And then number 3 is the methyl group. Now what you need to know when dealing with a Fisher projection is that the groups on the sides, in this case the H and the Br, they're in the front. So we need to reverse it. The group above and below, they're in the back. So keep that in mind. Now let's go ahead and count it. So starting from 1, going towards 2, and skipping 4, go from 1 to 2 to 3. If we travel from 1 to 2 to 3, notice that we're rotating in the clockwise direction, which would indicate R. But because H, number 4, is in the front, we need to reverse it. So therefore, this is going counterclockwise, or opposite to the direction of a clock. Therefore, this is the S isomer. So on carbon 2, keep in mind this is carbon 2, this is carbon 3. On carbon 2, we have an S configuration. So therefore, it's not going to be 2R. It has to be 2S. So now the last thing we need to do is find out the other chiral center, if it's R or S. So OH has the highest priority. If you compare this group with this carbon, oxygen has a higher atomic number. Next, if we compare this carbon and this one, there's no difference. So we got to move on to the next group. Bromine has a higher atomic number than the second carbon. So this entire group above, that's going to be, let's call it group number 2. H is number 4, and the ethyl group is number 3. So counting it from 1 to 2 to 3, ignoring 4, this appears to be the R isomer. But we need to reverse it since group number 4, in this case the hydrogen, is in the front. So because it's in the front, we're going to reverse it, and now it's going to be S. So it's 2S and 3S. Therefore, answer choice A is the right answer. Number 28. Which reaction will produce a meso product? Go ahead and pause the video, work on this problem. It turns out that the answer is B. Now let's talk about why. Let's go through each one. So here are a few things that you need to know. Let's say if you have a cis alkene plus a syn addition reaction, this will lead to a meso product if the product has a line of symmetry. So that's important. If it doesn't have a line of symmetry, then this will lead to a pair of enantiomers, or potentially even diastereomers, depending on the structure. But let's assume that we do have a line of symmetry for all of these examples. It's going to be a meso product. Now, if we have a cis alkene and let's say an anti-addition reaction, this will lead to a pair of enantiomers. So I'm going to write En for enantiomers. Now, let's say if we have a trans alkene plus, let's say, a syn addition reaction. This will also lead to a pair of enantiomers. And if we have a trans alkene plus an anti-addition reaction, this will lead to a meso product if there's a line of symmetry. So let's consider the first reaction. So here we have a trans alkene, and we're going to react it with potassium permanganate under basic conditions as indicated by the base hydroxide. The temperature is going to be low and the concentration is also low. So this reaction under cold dilute conditions will produce a diol, and this is a syn addition reaction. So the two alcohol groups will be on the same side. So this is going to be the product. But notice that we don't have a line of symmetry. And a trans alkene plus a syn addition reaction would lead to a pair of enantiomers. So the other product that you can draw will look like this. So we get a mixture of two products for this reaction. So that's what we can eliminate answer choice A. Now let's focus on answer choice C. We'll get back to B later. So we have cyclohexane, which you can view it as a cis alkene. And we're going to react it with bromine in carbon tetrachloride. The solvent carbon tetrachloride is inert, so you don't have to worry about it. So we have a cis alkene and an anti-addition reaction. This will lead to a pair of enantiomers. Because it's anti, we're going to put one bromine atom in the front and the other in the back. And as you can see, we do not have a line of symmetry. To draw the enantiomer, simply reverse the chiral centers. And so this is going to be the product of this reaction. Now let's move on to part C. So this time, we're going to react cyclohexane with water under acidic conditions, which is equivalent to H3O+. So the only thing that's going to happen is the alkene will be replaced with an alcohol. And we're going to add one OH group. And as we can see, the carbon that has the OH group is not chiral. The left side is equivalent to the right side. So therefore, we get a single product. And it's not a meso product. We only have one chiral center. We don't have two chiral centers. Now let's talk about answer choice B, which is the answer. So we have a trans alkene and an anti-addition reaction. This will lead to a meso product if there's a line of symmetry. So one chlorine atom, we're going to put it in the front, and the other one, we're going to put it in the back, facing the same direction initially. Now single bonds have free rotation, so we can draw a different conformant. So if we change the conformation by rotating this molecule, the Cl that was in the back is now in the front. And so notice that we do have a line of symmetry, which means that this is a meso product. Number 29, predict the major product of the reaction shown below. So we're reacting 1-butanol with pyridinium chlorochromate. So we have a primary alcohol, and which of these products will be the product of the reaction? Are we going to get a carboxylic acid, an aldehyde, an alkene, or an alkane? Chromium trioxide is an oxidizing agent, so it won't be reduced into an alkane, and we're not going to get an alkene. It turns out that this entire reagent is equivalent to PCC. PCC converts primary alcohols into aldehydes. Now you don't need to know the mechanism of this reaction, but you simply need to know what this reagent will do. If you have a secondary alcohol, it can oxidize it into a ketone, but know that it will convert a primary alcohol into an aldehyde. So C is the answer. PCC is a mild oxidizing agent. Now if you have a strong oxidizing agent, it can oxidize the primary alcohol to a carboxylic acid, but PCC won't take it that far. Number 30. Which reagent will produce the product shown below? Is it going to be A, hydrogen gas with a platinum catalyst, B, deuterium gas with a palladium catalyst, C, hydrogen gas with palladium mixed with calcium carbonate, or D, sodium metal mixed with liquid ammonia? Which one will convert the alkyne into a transalkene? So we can draw the alkyne like this. So the alkyne has 5 carbon atoms. Let's call this carbon 1, 2, 3, 4, and 5. Now what's going to happen if we add hydrogen gas with a platinum catalyst? This will simply convert it to a 5-carbon alkane. So we could eliminate answer choice A. Now what about answer choice B? What if we add deuterium, and what's going to happen if we use a palladium catalyst? Well, this will be reduced to an alkane, but by means of the addition of deuterium atoms instead of hydrogen atoms. To convert the alkyne to an alkene, first we need to add 2 deuterium atoms. Now, it won't stop here. This will continue. To go from the alkene to an alkane, we need to add 2 additional deuterium atoms. So this is going to be the product of answer choice B, which is not the answer that we're looking for. Now what about mixing hydrogen gas with palladium over calcium carbonate? What's going to happen? This is basically the Lindlar's catalyst. The Lindlar's catalyst is basically hydrogen gas using a palladium catalyst, but it's a deactivated palladium catalyst. It's deactivated once you add an ionic compound to it. Instead of calcium carbonate, you can add barium sulfate. So if you see palladium over barium sulfate, this still represents the Lindlar's catalyst. And what it's going to do is it's going to convert it into a cis alkene as opposed to a transalkene. So this is the product of the Lindlar's catalyst, using this as the reactant. So we can eliminate answer choice C, which means that we know the answer has to be D. If you add sodium metal with liquid ammonia, it's going to give us the trans product. Now you can use another alkaline metal. It doesn't have to be sodium metal. You could use lithium metal with liquid ammonia. It will lead to the same product. So D is the right answer.